So hey guys, welcome back to the channel. This is a physics buddy. This is going to be the lesson 7 of unit 5 forces and motion. In this video we are going to cover Newton's third law of motion. We will talk about contact forces such as normal and tension, and we'll also see how FBDs are drawn. Apart from this channel has already covered different units from honors physics curriculum. If you are new to the channel, make sure you subscribe to it and do check out those videos. Whenever we are learning something new, it takes time. What you have to do is you have to devote time. So do watch this video for a few minutes to understand the value of these questions, and let's get started. Make sure you write each and everything. Let's do this. So far in the classes we have discussed Newton's laws. We explained what is Newton's first law, and then we talked about Newton's second law. After that, we just came to know about what important property of Earth, like it has that nature of attracting things towards each other. So what we actually call that force with which that Earth attracts things towards each other is something we call gravitational force. So if we define gravitational force, so it is one of those universal forces which are there in our planet as well. So this is one of those fundamental universal forces. This forces, you can say, present everywhere in this universe. And what this force says that whenever two bodies have certain mass, so there is one such nature that every body possesses, that is of attracting another body. And that attraction force of attraction is directly proportional to product of masses, and it is inversely proportional to the distance of square between them. If I assume it is r, so it is going to be r square. When I combine both the equations, we get force is something which is directly proportional to product of masses, and square of inversely proportional to square of distance between them. So from here it came a constant which is called universal gravitational constant, which is supposed to be represented by g, and this g has a value 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. That is the SI unit for this g. What you need to understand here is, like, as the distance increases, this g changes. For example, if this object is placed at r distance, like this m2, if I just push it a little back at some r2 distance, so in both the cases, the force acting in the first case will be more in comparison to the second case. Why? Because it is inversely proportional to r. So as r increases, the force of attraction between the two bodies will decrease. And here comes this one such thing which is called gravitational field. So on the basis of this observation, we can define gravitational field as something which shows the possibility of a particular object or a particular mass to attract another object or mass placed at a certain distance. So it defines that factor that by which a mass is going to attract another mass. So it is something which is also depend upon the distance, like at what distance we are actually calculating this field. So this gravitational field is something which is directly inversely proportional to distance again. If it is at more distance, the field will be less. If it is lesser distance, the field would be more. But in case of Earth, we talked about that acceleration is supposed to be constant, that is 9.8. Then why we are taking this acceleration as constant if there is a field? Why we are taking this g as constant throughout the surface of Earth, whatever height at object is, whereas this gravitational field is a function of distance between the objects. So here comes this understanding that the Earth is supposed to be of radius, I would say 6,400 kilometers, or it is approximately 6.4 times 10 to the power 6 meters. So it is huge. This distance, you can say radius is huge. So if you are talking about any object which is at the surface, above the surface of Earth at a height of, let's say, 100 meters even, in comparison to this distance, this 100 meters is almost nothing. So if it is nothing, then only we can take g as 9.8, although it do change with change in height on the surface of Earth. So this whole thing is something which is related to gravitational force. In order to understand it, we need to know about this, because this is something which can be asked very easily, that if g is not supposed to be constant, why we used to take it as 9.8 everywhere on the surface of Earth? Because the distance at which we are observing the object is supposed to be very smaller in comparison to the radius of Earth. So that makes g constant near the surface of Earth. Whereas if it is like 200, 300 kilometers away above the surface of Earth, then g must be different. That is what we need to understand. So here comes the third law, finally. So now we need to talk about Newton's third law, because Newton's third law is reason for most of the events that take place on Earth. So according to Newton's third law, it is a very basic and common statement. We have learned it like hundred of times. So every action has equal and opposite reaction. This is what Newton's third law says. Like whatever the object there is, m1 and m2, let's say. So if they both are moving towards each other with certain velocity, at the time of collision between the two objects, the force of action by one such object must be equals to force of reaction by another object. So this F12 is always equals to negative of 21, whereas this negative sign shows the direction between action and reaction forces. So this action force is something you can say which is given, or you can say which is applied by the first object, which is might be moving very fast. So if this thing is valid here, it must be valid everywhere, because this is what law is. If it is a statement, it should be valid in all the circumstances. So let us try to understand few cases here regarding the Newton's third law. So I guess we should go with case one. Suppose I have put an object of certain mass onto the surface of Earth. So what will happen is the surface of Earth, or you can say the Earth, is actually attracting that object towards itself with a certain force we called weight, and that weight is something given by mg. We already learned about its property in the previous classes, so you can refer to the recordings if you miss it. So weight is nothing but mg. So here this weight is acting as nothing but action. So in order to react onto this action, the surface of Earth or the object whichever on the surface it is placed, the surface will definitely show some reaction, and that reaction is something which is given by normal force. This normal force is nothing but a reaction force which always acts onto the body in order to cancel out the force acting onto the surface, that is mg. Otherwise, if this normal force is not there, what would happen? This object will definitely sink into the surface, which is not the case because there is enough normal acting onto the surface, which is keeping this mass in a balanced state, you can say. So every action has an equal and opposite reaction. This is what this case shows us. Similarly, let me just show you another case, introducing you to another type of force that you might encounter in upcoming units. Suppose there is a spring, and what I does is I applied some external force onto this spring. Because of this extension, what would happen is the spring will try to apply some other force called spring force, which is in opposite direction of this external force. So why every time this is acting? Because spring is something which shows this property that every action, whichever we are doing, there must be a reaction. And this spring force is always equals to the external force which is applied. If this external force is more, let's assume, so spring force is less in that case, so what would happen is spring will break. But till the situation where the external force is within the range of this spring force, it will always equals to the external force. So Newton's third law has a lot of application here, and let's talk about one such application. So we need to understand this thing that it is valid everywhere. All right then. So let us assume that example once again. If there is an object which is above the surface of Earth, let's say this object has some mass m, I'll assume, and the Earth has some mass me, let's say. So what happens here is we always know that this Earth is pulling that object of certain mass towards itself with a certain force. So you can call it as F12. So according to this law, this object is also trying to apply some force onto the Earth, and it might be F21. And these two forces, according to the third law, should be equal. So what I want is that you should think it in this way. Why not Earth move towards the object if it is also applying the force? Why always that object is moving towards the Earth? That is the thing that should come to our mind. So in order to understand this, that why only object is seems to be moving towards Earth, but not Earth is moving seems to be towards the object, because of the mass. Mass of Earth is huge, very huge, whereas mass of the object is very less. So if the force is same, according to second law, what is the force? Force is nothing but the product of mass and acceleration. So I can say that the mass times mass of Earth into acceleration of Earth must be equals to mass of object into acceleration of object. So if we consider this above question, that mass of Earth is very huge in comparison to mass of object, so can I say that acceleration of object is going to be very huge in comparison to the acceleration of the object, Earth?
Yeah.
So that is the reason why Earth doesn't seems to be moving towards object. But yes, the forces are equal. Whatever force Earth is applying on that object, object is similarly applying the same force.
Okay.
So that is what third law says. So let us talk about certain forces. First, we're going to talk about some field forces. These are non-contact forces. They always act whether there is a contact or not. So This is something mg. We already talked about it. What it is? It is weight. Let me just give you a little idea about it once again. So magnitude of weight is always mg. Like whatever the object is times that gravitational field, it is going to be the magnitude of the weight. Similarly, if I talk about the direction of weight, like how it actually acts. So weight always acts perpendicular to the surface of Earth. So we talked about that thing also. I gave you two ideas. If the Earth is supposed to be like that, mg is acting that way. If Earth is supposed to be like that, the surface is a little bit inclined. In that case also, mg is going to be perpendicular to the surface of Earth, just like in first case. So we already talked about it. Here comes this normal reaction. That is an important thing. And that is the main topic that we need to learn in today's lesson. And Newton's third law as well, because normal reaction came into existence because of Newton's third law only. If there was no such law, maybe the force might be there, but we are not going to study it like that. So normal reaction is something which is basically an action to the situation, or you can say a reaction to the contact. So it is generally called a contact force. So contact forces are those forces which require physical contact. So what is this normal reaction? We'll simply say when two surfaces are placed against each other, there must
Mm.
be a contact force called normal reaction acting from it. So we do have certain cases to discuss that in which case what normal is going to be. It is a reaction force, so we'll calculate based upon the action. So it has no such formula to be precise, but yes, it has certain things. So let us see a few examples and try to understand what is a normal reaction in each case. So here's the first thing, or you can say the first illustration to be precise. Now, whatever chapter we are left with, it's something which is more difficult to learn in terms of theory only, because we need to talk about certain illustrations, or you can say the forms of how force is actually acting. So in that case only, the normal reaction can be represented. So first of all, let us try to understand that what is normal in these cases. Every time we are going to show these forces like mg, normal, whatever other force you might learn in future, these forces are represented through a diagram, and that diagram is called free body diagram. So these free body diagrams actually help us to understand that in which direction what force is acting. Like let us start it from the very basic. So far, we have learned about weight, and we know that weight always acts towards the center of the earth. So for m1, weight is going to be acting downward like that. Similarly, for m2 also, weight is going to act like that in the downward direction. We can write it as m1g and we can call it as m2g. Because of these mg, there will be a reaction force, which is supposed to be, I could say, n1 for the first object and n2 for the second object. But what is this? There is a force which is acting in a horizontal direction. So there must be some normal reaction acting between these two masses, like onto this surface. So if it is acting onto this surface as well, we need to understand that what it is going to be. So there must be, if there is some external force if acting on this direction, so m2 will apply a normal force on m1 like that. So you can mark it as n3. So this n3 is going to be equals to this external force, whichever it is acting. Similarly, n1 is equals to m1g and n2 is equals to m2g. So these are the magnitude of each and every normal acting here. That is what we need to understand.
Mm.
Does this make sense?
Yeah.
Another case. So again, we have to show that how normal is acting. And in order to do that, we need to understand the direction that how normal actually acts. So we already talked about this, that normal acts perpendicular to the surface. Like what? To the surface on which it is kept. Mg is something which acts towards the center of ground, center of earth, whereas normal is something which is always acting perpendicular to the surface. So in these cases, if I just draw the direction of normal, so first of all, we have to figure it out that how many contact points are there. So there are two contact points. One is this and another is this. So the normal in this case must be acting perpendicular to the contact surface like that. So I can mark it as NA, and there must be some normal force acting in this direction from this second point of contact, that is B. And this must be acting this way, which is called NV. So we will learn that how this NB and NA can be calculated, but when it is required. As of now, we need to understand that how they actually acts. Did you understand it?
Yeah.
So another case. So in this case, I guess you should try this out and tell me how it is going to be.
Mm.
It is not the same. Remember, this figure and this figure is a little different. So these are the point of contacts. And now try telling me that what it is going to be, how normal must be acting, what is the direction of normal reaction.
Mm. So you're applying upward force.
See, for B, it is going to be again perpendicular to the surface. I
Yeah.
can write it as NB. But for A, it is going to be like that. Why? Because if you make the tangent to this point A, it is going to be drawn like this, the way it is kept. So the normal is going to be perpendicular to it, like that. So that is something we need to understand, that how normal reaction actually acts on the system or in the system. If I assume this is an angle theta. Another case. Now this is interesting. This is something which you need to remember, because this is something which which we will be using in the later on days, although you know it. So here we need to understand that how normal is acting. So first of all, in order to actually mark normal, what we can do is we can simply just make x and y axis through this mass. It will help you understand basic things. So we always know that from this mass, weight always acts in downward direction like that. So mg must be acting downward like that. But the normal reaction is always acting perpendicular to the surface like that. So how we are supposed to draw it? We are supposed to represent it like that. So this is going to be normal because it is perpendicular to the surface. You can just verify it, that whether it is perpendicular to the surface or not, taking this line, considering this line. So it is going to be perpendicular to it. But the case is we have to find, let's say, how this normal or what this normal is going to be. So what we can do in order to find it, let us try to do that. Let us try to figure it out. So one thing we learned in vectors, that vectors are something which has component, which has two components, and these two components are perpendicular to each other. So can we find any component of this weight acting on the opposite direction of normal along this line, along this red line? We can try it out. So how can we do so? So this is angle theta. So it is going to be 90 degree. So this angle is automatically going to be 90 minus theta. So this is something I can write it as theta. Does it make sense?
Mm-hmm.
This is mg. This is theta. So in the earlier classes we talked about that how component is given. So this is mg. Just remember, whatever component is along with theta is going to be cos component. So it is going to be mg cos theta. Wherever the component away from theta is simply called mg sin theta. So here in this figure, mg must have a component along this direction, which is going to be mg cos theta. And there must be some force acting in this direction, which is another component, which is mg sin theta. So this sin theta is something which is responsible for the movement of this whole mass down the incline, like that. Again, what we need to understand is that how forces are acting here. Although we are supposed to learn mechanics in one dimension only, but I gave you a little bit idea about that how it will behave if the two dimension, or you can say the second dimension came into play. So if you are able to understand these things here, the classes which you're going to do in your school, they are going to be super easy. Just try to understand and visualize each and everything here. It will make sense like too much when you are learning in the class once again. Then there is another contact force which is called frictional force. So I won't tell you much about it as of now. You just take this thing in mind, that frictional force is something which opposes the relative motion between the two surfaces. I won't say object, because if there are two surfaces in contact and they are moving related to each other, so they must be applying, or they must be acting frictional force between the two surfaces. It always try to opposes the relative motion. Again, remember this term, relative motion. We have to talk about the relative motion, and we have to discuss few things with this term, like relative motion. This is important. We'll talk about it in the later on classes. So next, here we have another type of force called tension force. So this tension force is something which acts in strings, I would say, in ropes, thread, wire, or whatever which can hold objects. So those force which are acting there between the two objects are something we call tension. So tension, what is tension? Let us try to figure it out once again. So let me just take you to another, you can say the same example which I gave you in the earlier classes as well. Suppose there are two people and they are playing tug of war. So we know that whosoever applies more force will win, or you can say the point will move towards that object or person. What you need to understand here is just imagine there is no person standing out there. So how this rope will be, like in what situation it will be? It will be like that, right? There is no tension in the rope. The rope will be in the slacked state, I would say. So the tension is something which came into existence when rope is fixed from both the ends, like in this case. If I apply the force in this direction, as the object is connected with another object through rope, so this rope will automatically have some tension between its end. And that tension is something which is represented in by T, and it is something which always acts in pair. Tension is something which always acts in pair in the opposite direction, like that in this case. So this tension is generally equals to the force if object is moving with constant velocity. Remember, if there is net force 0 on the object, so object is maybe at rest or it may be moving, but with constant velocity. So we discussed these things in the previous classes as well, if you remember, the properties of net force when we were talking about balanced forces once again. So just make sure during a month, you just take out those 5, 6 days someday where you are just going through those recordings once again. I would
Okay.
say just go at 2x, just watch
Okay.
it at least. So all those things which we have discussed, these are keep you can keep them in mind because everything we are learning in the next unit or in the remaining part of the syllabus, it is going to be interlinked with what we have learned so far.
Okay.
So just take out any 4, 5 days and just go through the videos at 2x. I would say just try to revise it, or even before the test, you can go through it. Like whatever topic you need to prepare for the test, just go through the recording, so it will help.
Okay.
So now let us try to understand how tension is actually acting in the different systems. So suppose there are two masses M1 and M2, and they both are connected to a string, and I just try to apply the force in the horizontal direction like that. So first of all, the question says to show tension forces along with other forces. So along with other forces, we have to show that how tension is acting. So the diagram which we're again going to draw is called FBD. Remember the term. We're going to use it a lot in the classes as well. So according to the FBD, first we draw weight. So here, weight is going to be M1G. For the second mass, it is going to be M2G. Also, they must be acting force from the surface. I can say N2. Similarly, here, I would say it is N1. So these are the two forces which we just learned. Apart from this, there must be a tension. So as this force is acting in the right direction, so tension must be acting in left direction like that. But if there is a tension, there must be a tension because tension always acts in pair. So these are the forces that are acting onto the system, and the diagram which we have drawn representing all the forces is something we call FBD. Another case, another question. So I would suggest this, you should try